Hello, everyone. Good to see you again. I hope all you are doing very well. In this video, I'm going to talk about effect, variation, and identification, which are what we have to basically look at in data before analysis. Before you start, don't forget to check out our course website for if there are readings and videos required for this lecture. In this lecture, I first start with a simple example where we cannot learn anything from data even with a good model. Then I'm going to define an action and its effect in a research problem. Next, I'm going to discuss variation, which is what we need to measure an effect, and identification, which is to distinguish the effect from others. And with an example, I'm going to illustrate a general procedure of identification using a crosstabs. Last, I'm going to wrap up with a realistic story of two people in a sales department. Okay, are you ready? Then let's get started. When I was a doctoral student, a chief sales manager visited my advisor and me with sales data. The manager wanted to analyze the data stored in a big data warehouse. The size of the data was really big at that time, so the manager simply thought that he needs a good model. And that's why he visited us. He wanted to learn about marketing models to analyze the data. But after taking a look at a small sample from the data, I found there was something wrong. Surprisingly, there were no price variations, and I quickly asked about the price variations in the entire data. More surprisingly, there were just a little price variations in the entire data. In this anecdote, I had data, and of course, I had a model good enough to analyze the data. But I was not ready to do research. More precisely, I couldn't do research. Why? This graph shows my expectation of the data. The sales team had collected data of price and sales, so I thought that we could apply a demand model to the data to describe the relationship between the price and sales. However, the actual data looked like this graph. The price variation was very small, so we couldn't find any evidence of demand response to a price change. There was no way to see whether customers are price sensitive, price insensitive. This short story tells us there is another step before actual analysis. That is, we have to take a look into data to see if there is enough variation to identify the effect we want to study. Before having a detailed discussion, let me clearly define the terminology first. As discussed, the main purpose of marketing research is to support managers' decision making. Usually, a decision making problem involves one or several possible options. From the marketing researcher's perspective, the decision-making problem is a research problem, and such a possible option is a marketing action. And marketing research provides empirical evidence, which is the evaluation of each option. The effect of an action is the change in evaluation caused by the action. For example, let's think about this research problem. Whether to discount the shelf price of a product. The marketing action associated with this problem is to discount for the product. And we can say that boosting sales is the effect of the discount because evaluation criteria, revenue and profit are generally functions of sales. Then the evaluation of this action is to measure how much the discount boosts the sales. In other words, measure the effect size. Here is another example. To which market to deploy our advertising? The marketing action associated with this problem is to increase ad frequency and spending in a specific market. The effect of this action we're going to look at is a change in sales due to the additional advertising effort. To measure an effect, what we need? If someone asks me to pick the most important one we need, my answer is variation in data. Let's go back to the first research problem. The action that involves the problem is to discount the price, and the effect of the discount is what we want to investigate. So, suppose that we gathered sales data at a discounted price. Can we measure the effect of the discount on sales? No, we can't. Because we know only the sales boosted, and there is no way to know the amount of additional sales due to the discount. Then, what do we need to know there? We also need what happened with the regular price, that is, the baseline sales. Subtracting the sales at a regular price from the sales at a discount price, we now can measure the additional sales caused by the discount. For the advertising effect, we need the same thing. We need sales data with regular advertising effort as well as the data with increased effort in order to measure the advertising effect. This implies if we want to look into the price effect on sales, we need to have a variation or fluctuation of the pricing data. Without the variation, for example, if we have sales data with a flat price, it is impossible to measure the effect even with any fancy advanced methods. But sometimes it is not easy to measure an effect, even though we have enough variation in data. Because there are multiple factors given or decided, and thus the effect of an action is generally mixed up with the effects of the others. Here is an example. Let's think about beer demand. There is a customer who bought beer more than before because of a price discount. And there is another customer who bought beer more than before, but different reason. Because it was 4th of July. So, sales of beer depends on both the price discount and seasonality. Identification is a procedure to separate out the effect we investigate from other effects. In the beer example, if we want to identify the price discount effect, we need to get rid of potential confounding factors such as seasonality. Then, how to identify? Identification of an effect is similar to conducting an experiment. When we do an experiment to investigate an effect, we design a treatment group and a control group with only one difference between them. The treatment or action involves the effect, and any other factors must be constant or randomized. Identification of an effect requires the same conditions in data. We need two groups of observations where the action variable is the only one that distinguishes between the groups. Thus, the first step to identify an effect from others is to find those groups by drawing a cross-tabulation, for short crosstabs, or contingency table. This is an example. Beer weighing. For simplicity, suppose that there are only two price levels, $8, which is the regular price, and $6, which is the discounted price. The first table shows the number of observations and total demand in data by seasons, like winter and summer. And I reshaped the first table into the second table to show the average demand per observation by season price combinations. In this example, the table shows we observed the regular price only in the low demand season and the discounted price only in the high demand season. We can easily observe this data pattern, so-called countercyclical pricing, for seasonal products in reality. But the problem is that we cannot identify the price discount effect from the seasonality in this case. In the second table, average demand increases from 2 to 2.78 when price changes from $8 to $6. But at the same time, season also changes from low to high. In other words, there are only two groups of observations, and price is not the only one factor that distinguishes between the groups. That is, we cannot know where the demand increase came from. How about this case? Suppose that we now have regular price and discounted price observations in both seasons. As in the second table, we are now able to separate the price effect from the seasonality. First, let's look at the group of regular price observations versus the group of discount price observations. Simply each column. For each price level, an enough number of cases were observed in each season. 60 of regular price in low demand season, 80 of regular price in high demand season, and 75 of discounted price in low demand season, and 90 of discounted price in high demand season. These well-balanced numbers of observations imply that the price is the only one factor that distinguishes between the columns. The seasonality can be regarded as randomized. Next, let's look at the rows. The group of low demand season observations versus that of high demand season observations. In the same manner, we can find that the season is the only one factor that distinguishes between the rows. There, we can identify each effect from the other. This table shows that the price discount effect exists and the effect can be identified from other effects. Here, to draw this table, we have not used any advanced techniques. We've just summarized and reshaped the data. So, this type of tables is usually called model-free evidence. Most researchers in most studies spend most time to find the model-free evidence because it intuitively shows what we can learn from data. Once we successfully find model-free evidence for an analysis, applying model and advanced techniques to data is an activity to confirm the effect and exactly compute the size of the effect. As an example, I'm going to talk about an interesting story. This is a story of two people, Mr. Mistake and Ms. Perfect. Mr. Mistake is a sales manager of a grocery store, and Ms. Perfect is a data scientist. I found a weird thing in the sales data, said Mr. Mistake. Wow, what do you have? Said Ms. Perfect. This baby care product demand increases as price goes up. See, said Mr. Mistake, and he showed an estimation result. See, the price coefficient is positive, said Mr. Mistake. Mr. Mistake, could you tell me more about the data? What is the quantity and what is price? Asked Ms. Perfect. Sure, I summarized purchase volume and price by week and brand. For example, 60 units of brand A were sold in the week of June 6, 2005, and the average price of them was 13.8, answered Mr. Mistake. Then, what's your opinion? Do you think it is correct? Alright, let's first think about what Mr. Mistake did. He examined the price effect on sales, but regardless of brand. In this table, I split the data at the median of price, regardless of brand. The first row is for low price observations, whereas the second row is for high price observations. The first column is the average sales quantity for each price group. And as you can see, the higher the price, the more the sales. Average sales of low price observations is 24.6, whereas sales of high price observation is, on average, 44.9. It seems that this table is consistent with Mr. Mistake's finding. But this table actually shows that Mr. Mistake is wrong. The second, third, and fourth columns show the number of cases for each of the brands. All of brand C are low price cases, and almost all of brand B are high price cases. That is, we cannot know whether the average quantity 24.6 came from the low price or brand C. Let me graphically illustrate what Mr. Mistake did. This is the scatter plot of price and demand quantity pairs in his data. And this is Mr. Mistake's regression line. Many points are far from the line, but it seems that the line goes through the middle of the data points. But when we consider the brands at the same time, what happened? Black is the color code of brand A, and red is that of brand B, and blue is that of brand C. Group-wise, you may find negative trend, not positive trend. And this is Mi's perfect solution. She gets rid of the brand effect by computing median by brand. Those well-balanced numbers of observations indicate that the brands are randomized between the price groups, and the lower the price, the more the sales, as our conventional wisdom. Alright, that's all I have in this lecture. After watching this lecture, please check out our website again for if there are additional readings and videos required or strongly recommended, online quiz assignment, and hands-on exercise in our software. Then, see you in the next lecture. Bye-bye.